All right, so we'll go ahead and share my screen here. And I apologize to people still logging in. We don't have a lot of time, so I've just kind of started a little ahead of the game here. All right, can everyone see my Jupyter Hub screen? Great. Okay, so first of all, you may need to sync your curriculum for this. If you need to do that, you can go to a terminal here in the launcher and just type sync curriculum. Basically, if you go into this curriculum directory and then look at, there should be a Pytorch tutorial directory here. Whoops.
Sorry, I think we're only seeing the page with the introduction.
Sorry, you're seeing, what are you seeing? You're not seeing my Jupyter Hub?
Yeah, only the Jupyter notebook.
So okay, that's fine. That's what you should be seeing. So you see this this window where I synced the curriculum?
No, only the notebook quick introduction.
Oh, that's funny.
It kind of looks like a video froze.
Oh yeah.
Okay, let me try again. Are you seeing my my Jupyter Hub now? Okay, sorry about that. Let me start over. Basically, if you open up Jupyter Hub, it should look like this. I was just letting you know that you may need to open up a terminal and type sync curriculum, just to get make sure that you have the Pytorch tutorial. I'm just going to close this because I don't need it anymore. But once you sync the curriculum, you should be able to go into the curriculum directory, and there should be a Pytorch tutorial directory here, and there's a notebook in here that has the tutorial in it. Now, I'm not going to open this. I'm just going to kind of live code through this tutorial. So I'm just going to open a blank notebook, and you should feel free to do that as well. But if you come back to this later and you want to kind of go through the tutorial on your own, especially considering that we probably won't get through everything, you can look through this notebook, and it contains a bunch of documentation and extra information that should help you understand things. Okay, so for anyone who's not already familiar with Pytorch, Pytorch is a machine learning library, and it's one of the two kind of preeminent machine learning libraries out there right now, the other one being TensorFlow. Pytorch has been around for a long time. It's not just a Python library. It's been translated into some other languages at this point, and it's very efficient and effective at what it does. And we're just going to be talking through some of the some kind of examples of how you can use Pytorch today. So to start with, we're going to import Pytorch, and the name of Pytorch is actually just Torch. So we can import that. And then we're going to import some submodules of Pytorch, because pretty much Pytorch is made of a lot of different pieces, and we'll need to use a lot of them in this tutorial. So from Torch, I'm going to import NN, and NN stands for neural networks. So there's a submodule of Pytorch that contains neural network code. And also, just as a reminder, I'm assuming a little bit of a slightly more advanced Python knowledge in this particular tutorial, but if I go through things a little too fast or do something that doesn't make sense, please interrupt me. We're not a huge group, so feel free to ask questions. In addition to importing this neural network library, I'm going to import a particular class, a Python class called data loader. So this is from torch.utils, utils.data import data loader. And then we're going to import just a couple more things, and I'll explain these when we get to using them a little bit later in the tutorial, but for now, just trust me that we'll need them. So there's another library called Torch Vision, which is actually technically separate from Pytorch, although it's part of the greater Pytorch environment of tools. And it's basically specifically a computer vision library. And we're going to do an example that involves computer vision in a little bit here. So from the Torch Vision library, we're going to import datasets. And datasets is actually a module that contains a whole bunch of data sets that are like kind of pre-encoded into Python, so we don't have to worry about loading in the data. And then finally, we're going to import from torch vision.transforms a class called toTensor, which I'll also explain in just a bit. Once again, for now, you just need to trust me that we'll need it. And then finally, we're just going to import matplotlib.pyplot, and this is just so we can plot some visualizations of what we're doing as we go. Okay, so the Pytorch library revolves mostly around a kind of core data type called the Pytorch tensor. Now, you may recall from algebra that tensors are essentially a generalization of vectors and matrices. So a vector is a rank 1 tensor, a matrix is a rank 2 tensor, and if you have like a cube of data, that's a rank 3 tensor. So tensor is just kind of a generic term for some block of numbers. And it can be as simple as a rank 0 tensor, which is just a number itself. That's what they are mathematically. In Pytorch, tensors are a lot like NumPy arrays. And in fact, they use NumPy arrays in the back end to kind of store the tensors. But for the most part, tensors act just like the NumPy library. So just as an example, let's go ahead and make a tensor. And you might recall that NumPy has
I got a question.
A function. Oh yeah, go ahead.
Sorry. Are these the same, like, I don't know much about like TensorFlow, but are these the same like objects that are used in TensorFlow?
So honestly, I've never used TensorFlow, so I can't answer that question for certain, but I would be really surprised if TensorFlow doesn't have a similar class for something like tensors. It's possible they don't call them tensors, they might call them arrays or something like that, but I would guess
I think they're called tensors there.
Okay.
That's all.
Yeah, that would make a lot of sense. Yeah, they're probably very similar. And in fact, in general, my guess is that Pytorch and TensorFlow contain a lot of the same utilities and may just be called slightly different things. Okay, so you might recall that NumPy has a function numpy.zeros that lets you make like an array of zeros. And Torch actually has the same function. So if we want to make a matrix, a 10 by 3 matrix of zeros, for example, we just pass a size 10 by 3 to this zeros function. And I'll go ahead and put U so we can see what it contains. And this gives us back a tensor of zeros. Now, had we done this in NumPy, we would have gotten something very similar. It just would have been an array instead of a tensor. So you can see that NumPy arrays and Pytorch tensors are fairly similar. And in fact, most NumPy functions also exist in the Torch library. It's just that instead of working with NumPy arrays, they work with Torch tensors in the Torch library in Pytorch. And just to kind of demonstrate this, we can use tensors in a very similar way that we use NumPy arrays. So for example, we can assign all of the first column to be ones using the same syntax we would with a NumPy array. And we can do simple arithmetic. For example, U minus half times 3 will give us a bunch of 1.5s. Positive 1.5 in that first column that was 1 and negative 1.5 in other columns. So basically we can do simple arithmetic and we can call simple NumPy-like functions using the Torch library. It just sort of duplicates these this functionality that NumPy has. Now that may seem a little funny, like why would Pytorch duplicate this functionality? And there's a good reason for this. In fact, NumPy arrays aren't totally compatible with Pytorch tensors. So for example, if we make an array, a NumPy array of zeros, just like this array we made a second ago, and then we try to use the torch function to find the mean of that array, we're going to get an error because the torch mean function doesn't understand NumPy arrays. Instead, it only understands torch arrays. So like that torch array we made a minute ago, we can take the mean of it. So this is just something to know. You need to be a little careful when using Pytorch and NumPy tensors and arrays interchangeably. They can't actually be used interchangeably. So just something to be careful about. And now the reason for this is because Pytorch tensors are sort of like NumPy arrays on steroids. They you can do all the stuff you can do with NumPy arrays in Pytorch, But in addition to just giving you the results of whatever calculation you ask for, Pytorch tensors will keep track of how that calculation was made. So you notice that this torch.mean function didn't return the number 0.33. It returned a tensor of the number 0.33. And this tensor has, as part of its data, basically some information about how it was calculated that says, oh, we took the mean of this particular tensor. That's how we arrived at this number. And the reason that Pytorch does this is because when you're doing optimization, or when you're training neural networks, or when you're doing a minimization, anything like that, most of the time, the way that the optimization algorithm converges towards a correct answer is by looking at the gradient of whatever you're calculating and stepping along the gradient towards whatever the minimum is. I just wanted to show you something in case you're not familiar with this basic idea. This all kind of derives from a method for finding zeros of functions that was developed by Newton, called Newton's method. This is an animated GIF that shows it. It'll start over here in just a second. But the basic idea is you can evaluate some curve or function at some point, like x1. You can find its derivative, which is that red line, and you can find out where the derivative is 0. And then you can repeat the process, and you can continue repeating the process until you eventually find a number very close to where the function is 0. This is a process, and I apologize for going through this very quickly, but we just don't have much time today. This is a process that is used by a lot. Any gradient descent optimization algorithm uses this basic idea to figure out how to minimize the function. You basically find the derivative or the gradient at some particular point, and you follow along it until you reach the point you're looking for. This is a very common method, and it's used in training neural networks. It's used in gradient descent optimization. It's used all over the place. And so what this means, though, is that you need an efficient way to calculate the derivative or the gradient of whatever function you're trying to minimize. And that can be a very hard thing to manage on your own, especially if you're optimizing something that isn't very simple. So as soon as you start having like distance calculations or sines and cosines or anything more complicated than just some simple arithmetic, calculating a gradient can be very hard. And if you have a high dimensional problem where you're calculating the gradient over, hundreds or thousands of dimensions, it gets really hard. But Pytorch can do all that for you, and mostly it does it behind the scenes without you having to really think about it. Okay, so I want to pause there and ask if there are any questions, because I know that we just covered quite a bit in a pretty short amount of time. So any questions so far? Okay, well, we'll keep going, and please shout out if you have questions. All right, so just to kind of demonstrate a little of how this works, we'll go ahead and do like a toy example. So let's suppose for a minute that we are trying to find, we've got some curve, and I'm going to just write out the curve. Here's our curve. I'm writing this out in a markdown cell, and I'm going to write it out using some LaTeX notation. Basically, our curve is f of t equals x of t comma y of t. So this is a parametric curve. And I've just come up with some kind of arbitrary definitions for these functions x of t and y of t, but we're going to have this be sine of t minus 1/2, and y of t is going to be cosine of t, 2t plus 0.75. I'll render that so we can see what it looks like. So this is a parametric curve, and I'm just going to write a function here called curve of t, and we're just going to define this curve. So x equals torch.sine of t minus 1/2, y equals torch dot, and sorry, I wrote this wrong. This should have been cosine of t times 2 plus cosine of 2t. So sine of t times 2 plus torch dot cosine of 2 times t plus 0.75. And then we'll just return x and y. So I'm going to go ahead and plot what this looks like. Let me go ahead and run that. So To plot what this looks like, I'm going to make a variable t. I'm going to use the torch.linspace function. This is pretty much equivalent to the numpy linspace function. It takes a minimum value and a maximum value and the number of points that you want between those values, and it gives you back a vector. So we'll say we'll go from 0 to 2 times pi, since we're using sines and cosines. And we'll just say 100 points in between them. And I want to show you what that looks like. That's just a vector that goes from 0 to 2 pi with evenly spaced points between them. What we can do is we can say, let's get the x and y coordinates for our curve at those points. And then we can just plot them. So I'll plot it as a black line. And then just to make it a little easier to kind of see the plot or where things are on the plot, I'm going to add a couple lines that just represent the x and y axes. So we'll plot from -3 to 3 on the x, 0 for the y, and the same but for the y-axis. Or yeah. Okay, so this is what our plot looks like. It looks sort of like the Star Trek symbol, communicator symbol. This is just an arbitrary curve. And let's suppose that we're trying to figure out which point on this curve is closest to the origin, is closest to the value 0. That's kind of a difficult problem to solve because we have a parametric curve. But we can do this using optimization pretty simply in Pytorch. So when we define an optimization problem in something like Pytorch, we usually describe a loss function. When people talk about loss functions, what they're typically talking about are whatever function you're trying to minimize. So we have some loss function. We want to make it as small as possible. And when we make the loss as small as possible, we'll have found the value of t that minimizes whatever we care about. In this case, what we care about is the distance between whatever point on this curve and the origin. So we can go ahead and define a loss function in terms of t. The first thing we'll do is we'll get the value of the curve at point t. And then we just want to calculate the distance between the origin, 0, 0, and x and y. So all we need to do, we can say distance equals torch.square root x minus 0 squared plus y minus 0 squared. And then we can just return that distance. So that's our loss function. And now, just to kind of test it, we can say we'll make a tensor just containing the number 1.5. And we can say distance equals loss of t. And let's just print it out. So when t is equal to 1.5, that point along the curve has this distance from the origin. That's what this tells us. So if we find the minimum value of the loss function, we'll be able to tell which point along this curve is closest to the origin. And my guess is it's going to be somewhere around here. So to do this, actually, let me show you one more thing first. So we calculated this here, but let me show you how to get the gradient out, or the derivative. So what we can do is we can make a new tensor, t equals, again, 1.5, but we're going to pass an optional argument this time that says requires grad equals true. What this tells Pytorch is that our tensor, this particular tensor that we're making, is a parameter to some function, and we're going to need to know the gradient of that function in terms of t. So Pytorch should specifically keep track of the gradient with respect to this variable. So then, if we do the same thing, we can run a function that's called backward. And what the backward function does is it just calculates the gradient going all the way back up to whatever parameters we provided, which in this case was t. And we can tell t is a parameter because we told it that it had a required gradient. And then we can just ask for t.grad. And when we run this, it will tell us that the gradient at point t is 0.5118.
I've got a question.
Okay. Yeah, absolutely.
Is there like a default method that TensorFlow uses to calculate the gradient, Like,
Yeah, so, oh, go ahead.
and can you change that, or does it do it like intelligently?
So yeah, Pytorch is very smart about gradient calculations. I'm actually not sure if there's a way to change the way it calculates gradients, but gradients are all deterministically calculatable according to like the fundamental theorem of calculus. So there are pretty well-known algorithms for calculating these. What's great about Pytorch is that if you have like a lot of CPUs, it will automatically use all of them to calculate the gradients, and it will do it really efficiently. So in general, I've never needed to look behind these functions. They just seem to work really well most of the time. That said, if you have some special function that you think doesn't have is hard to calculate the gradient for or something, I believe there are bits of Pytorch that can do that. It's just that I've never had to interface with them myself.
Okay, cool.
Generally, this just kind of works. Any other questions? Okay, so let's go ahead and solve this minimization problem as an example. And I just want to emphasize additionally, we're solving a problem that's pretty simple. It's just got one. It's just got one parameter. But this method we're using would work just as well if Curve had like 100 parameters or tens of thousands of parameters. Pytorch is very efficient for high dimensional optimization. Okay, so let's go ahead and make an input tensor. This is what we're going to minimize. I'm going to give it the value 2.1 this time, and we need to tell it that we are going to be using the gradient, so we require the grad. And then the next thing we need to do is we need to declare an optimizer. So there's a whole library of optimizers that Pytorch knows about. In this particular case, we're going to use the stochastic gradient descent optimizer. So we can declare that by saying optimizer equals torch.optim. Optim is the submodule of Torch for optimization. SGD, which stands for stochastic gradient descent optimizer. We give it a list of our parameters, which in this case is just t, and then we give it one more parameter, which is the learning rate. Learning rate is basically a parameter to almost every optimizer in Pytorch, and it basically tells it how fast do I want you to try to find the minimum. This is a bit of a kind of magic number that you have to give these optimizers. If you give it a very high learning rate, like 0.1, it's going to try to take really big steps in your optimization, and it might go off the rails. And I wish we had a little more time to talk about this kind of behavior, but essentially in optimization, you can have problems where you're trying to learn too quickly and you zoom past the answer. Whereas if you're learning more slowly, it will take longer for you to get to the answer, but you'll at least find it. We're just going to give it a value of 0.05. This is actually a slightly high value. Typically, a good place to start is 0.01. But if you're having trouble with learning rates, I suggest you go read some of the other Pytorch tutorials about them. They discuss this in much greater detail. Okay. So next, what we're going to do is we're going to take a number of steps. We're going to have the optimizer take a number of steps, I should say, and we'll just do 20 steps. So I'm going to say 4-step number in range 20 for our 20 steps. And now inside of this loop is going to be 1 step for each loop. So the first thing we need to do is tell the optimizer that we're starting a new step. And the way we do that is by calling the zeroGrad function. And the reason we call this function to tell the optimizer that we're starting a new step is this basically says, okay, I know you might have some calculation of the gradient sitting around somewhere from last step, but we're starting over, so make it all equal to 0 so we can start again. Now that we've told it that we're starting a new step, we can just calculate the distance by calling our loss function. Now I'm going to print out a little diagnostic message here. I'm just going to say, here's the step number we're on, and here's what t is equal to, here's what the loss is equal to. And then that's just so we know kind of what's going on. And then we're going to call that backwards function so that it calculates the gradient for us. And then we don't have to deal with the gradient. We just tell the optimizer to take a step. And it'll do the rest. And once we've done 20 steps, I'm going to have it print t. This gives us a loss of t. So I'm going to go ahead and run this now. And it's really fast. What we can see is it takes a bunch of steps. You can see that t is changing and the loss is kind of slowly going down. It goes to about half of its original value at about t equals 2.6668 or so. And at the end, the final value is 2.6991 with a loss of about 0.43. Okay, so let's plot what that looks like. Let's go ahead and find the XY point for this particular value. And I just want to point out that t is still whatever value it found. So during that process, we minimize t, and now t contains the solution we found. So I can just I'm going to call them x naught and y naught are the minimized points. Now, there's a tricky thing here. I can find those points, and we can print them out. Whoops. But they're tensor values. So if I want to turn these into NumPy arrays, I have to call a function detach, and then I have to call a function NumPy. Now, the detach function is here because this tensor has a gradient stuff attached to it, and we want to detach whatever we're dealing with from that gradient data. Now, you don't always have to do that, but Pytorch will give you warnings and errors and stuff if you don't. So it's a good idea to, if you're converting to a NumPy array, always detach your Pytorch tensor first. This NumPy function then just returns the NumPy array that is represented inside of the Pytorch tensor. So this will convert x naught into a NumPy array. I'll go ahead and do that for the y naught as well. And if there are any questions about this, please pipe up.
Yeah. So does your tensor have like all the values at each step like included with it, or are those gone now?
No, those are not gone. It's a little hard to access them, but in the background, those steps that were used to calculate x naught and y naught are all still there. Yeah,
Cool.
They're kept track of. Yeah. Okay, so so first of all,
Hey, sorry.
Oh yeah, go
One
ahead.
question: is there a shorthand method for doing this detach from like in a faster way? There is no way like to convert this to NumPy directly.
No, not that I know of. This is pretty much the standard way of doing it. Yeah.
Okay. Another thing, could you go up just a second to the previous cell, like the one before? I am going to
This
take
one?
a screenshot. Yeah, just one moment. All right, thank you. Yeah, all right, took a screenshot.
Okay, so since we're running a little short on time, I'm going to copy and paste some of the next cell rather than type it out by hand. Apologies for that, but I just want to show you that this found the right solution. So here I'm going to paste a bunch of code. Here I'm basically just getting our whole curve again, that Star Trek communicator shaped curve, and then I'm going to plot it, and then I'm plotting those axes again. And then finally, I'm plotting the point we found, x naught and y naught, in our minimization in red, as just a dot. So when we plot this, we see that it found this point here, which is pretty close to the origin. And I do think this is the closest point in this curve to the origin. Okay, any questions about that? All right, so yeah.
I say no question.
Okay, great. So that was a very quick introduction to the basic idea of Pytorch calculating gradients. Gradients, I'm introducing this partly because this is like one of the core things that Pytorch does that's really important, kind of behind the scenes. But now we're going to switch gears and talk about neural networks. And neural networks also require these gradients to be calculated and use all of these methods we just used kind of behind the scenes. But Pytorch has a bunch of neural network tools that make a lot of this easier. to deal with, and you don't have to think about this in the foreground as much. So, okay, so we're going to do a little example here using an existing data set that we can get from that Pytorch torchvision.datasets module that we imported at the beginning. So I'm going to declare a variable training data, and we're going to get this from datasets.fashionmnist. So the fashionmnist dataset is a dataset of images, low resolution images of different articles of clothing and labels of what kind of article of clothing those things are. And what we're going to do is we're going to try to train a neural network to label clothing based on the pictures. So this is a basic computer vision application. So I'm going to pass a few parameters. The first is root equals data. This is just telling Pytorch it's going to download the data for us when we call this, and we're just going to tell it to cache it in a directory called data. I did this earlier, so for me this is going to go real fast. It will for you too, but it may print out a whole bunch of messages about downloading the data as it goes, and so just don't be alarmed about that. Since this is training data, we're going to tell it that it's training data with train equals true. We're going to tell it to download the data if we don't have it with download equals true. And finally, we're going to pass an argument transform equals to tensor. To tensor is something else we imported at the beginning of this notebook, and it's just basically a class that will convert whatever input we read in from the fashionmnist dataset into a Pytorch tensor. And then I'm going to declare one more variable, the test data, and I'm actually just going to copy and paste this because it's almost identical. So the only thing we need to change is that this isn't training data, this is test data. So we change train to false. So I'm going to go ahead and run this. For me, and by the way, you may get a warning here like this. You can totally ignore this. This is a version mismatch between NumPy and Pytorch, but it won't matter. So it may display a bunch of messages as it downloads the data for you, but hopefully that works. Any questions about this, or anyone have it not work? All right, great. So okay, so the Pytorch typically likes you to use this class called a data loader to feed data into neural network models. These are pretty simple. The reason that you use a data loader is that you usually want to give neural networks training data in batch, where like instead of giving it just one thing to train on at a time, you give it like, here's 64 images, train on these, and then here's 64 new images, train on these. So you typically want to load data in batches, and that's what this data loader class manages. So we'll declare a batch size as 64, and then we'll make some data loaders. And data loader is another one of those classes we imported at the top, but we basically just say we're going to have a data loader based on our training data, which with this particular batch size. Yeah.
Sorry, just a heads up. You missed an N on the original assignment, so this will probably, yeah.
Oh, thank you. Yes, let me just fix that. Yeah. Okay, thanks for pointing that out. Great, so we'll make one for the training data. I'm just going to copy and paste this for the test data to save a little time. Test data loader, we'll just need the test data. And these data loaders are pretty simple. There's not very many things they do, but the one thing that you can do with them is you can iterate over them, and they'll just give you batches of the data as you do that. So for an example, I'm going to say for XY in test data loader, and I'll just print shape of X dot shape, and shape of Y. It's a mistake. Y dot shape, and then I'll break because I don't want to do that for every element. I just want to do that to show kind of what they look like. So for our X value, which is the images, we can see that we have 64. That's the batch size, and then we have 1 by 28 by 28. So these images are 28 by 28, and they're 1 by 28 by 28 because they're grayscale images. They don't have RGB channels. If these were color images, they would be 3 or maybe 4 by 28 by 28. And then the Y is just 64 because Y is just a number that corresponds to the kind of clothing we're seeing in the image. So I'll go ahead. I'm just going to paste a key to the, this is just a key to the images, sorry, to the labels. So label 0 is a t-shirt, label 1 is trousers, label 2 is a pullover. You can also copy and paste these from that other notebook I pointed you to a second ago or earlier in the talk. But if you don't copy and paste these, it's not a big deal. You can just print the numbers for now. But we're short on time, so I don't want to type it all out. Okay, so I just want to show you what's kind of in these, what our data looks like. So I'm going to go ahead and plot here of just a few examples. So I'm going to make a 2 by 2 grid of plots. I'm going to flatten the axes so I can just iterate over them easily. And then what I'm going to say is for x comma y in the training data set. We want to go ahead and just, we'll just plot the first image. Sorry, the first 4 images. So we're going to iterate through so sorry, recall that when we iterate through the train data loader, we get back things that are batches of 64 images. So we're just going to iterate through the first 4 of these, and this loop will stop because there's only 4 axes. So once we get to the end of the axes, it'll automatically stop the loop. Sorry, this needs to be a zip. And we just want to take that particular axis and plot the image. And because these are just one channel by 28 by 28, ImShow likes to have a 28 by 28 matrix for grayscale. So I'm just going to say x iter 0. And I'm going to set the title to the labels. Now, if you didn't copy and paste this variable, you could just say a string of y instead, and it'll print the number, and that'll work just fine. And I'm going to turn the axis off just so it's a little easier to see. And then once
y iter.
Yes,
y
thank
iter.
you. You're right. Yep. Thank you. Yeah, that wouldn't have worked. Great. And then since we only want to do this for the first batch, we're just going to break after that loop. So again, I apologize. This is going a little fast. Sorry, I mistyped that. Subplots. I apologize that this is going a little fast. We just don't have much time in this tutorial this morning. I want to get through at least enough that you can finish the tutorials on your own if you want. So this is what the data set looks like. We see we have pretty low resolution images of various items of clothing and names for them that are our Y labels. Okay. Any questions about this data set so far? Okay. All right, so let's see if we can get through the rest in 6 minutes or so. So the next thing we're going to do is we're going to define our neural network model. So we typically define a neural network model in Pytorch by declaring a Python class. So we're going to say class neural network. And this neural network class is going to inherit from the module class in the Python neural networks, Pytorch neural network submodule. So you might recall that we imported neural networks earlier from Pytorch in the very first cell. So we're going to use neural network.module as the base class. And in a Pytorch neural network module, this basically a module can be either a whole neural network, or it can be just a layer of a neural network, or it can be a subset of layers of a neural network. It's pretty flexible. The only things we have to define are two functions. The first is the constructor, which is underscore underscore init underscore underscore. I'll define that in a second. And the second function we need to define is a function called forward, which takes a parameter x, which is just the parameters of our model. If we define these two functions, this will work as a neural network layer or as a neural network itself. So typically what you do is you define whatever layers of the neural network you're going to use in your init constructor, and you define you define the actual calculation in the forward function. So I'm going to go ahead first of all call the superclass. So this is just a line that calls the constructor of the module class. And that just needs to be called to make sure that all the module stuff is initialized. Then we're going to make a neural network flattened layer. So the reason we do this is because we need the neural network to take these images and flatten them into a flat tensor that it knows how to deal with. That wouldn't necessarily be the case in every neural network, but we're just making a very simple neural network. So we're going to start by flattening things because it simplifies some of the processing. Next, we're going to make what's called a linear rectified linear unit stack. So we're going to call this linear ReLU stack. If you're not familiar with the term ReLU, this is a rectified linear unit. It's a common operator or a layer of neural networks. And then, well, we don't really have time to talk about exactly what all these layers are going to do, but the basic idea is we're going to add just a few kind of typical neural network layers here. And we put these in what's called a sequential neural network object. Because we have a sequence of neural network layers and the data are going to flow through those layers in sequence. So we'll put a linear operator, which has 28 by 28 inputs. It's going to have 512 outputs. And that's what these parameters represent, the number of input parameters, and the number of output parameters. We're going to follow that by a rectified linear unit, which is going to have 512 inputs and 512 outputs. We're going to follow that by another linear layer, which has, sorry, I screwed up there. The rectified linear unit layer doesn't need inputs and outputs. This linear transform, however, does need inputs and outputs, and we're just going to have those be 512 and 512. So this is a linear transformation that takes something like 700 inputs and converts it into a smaller number of inputs. This is just another linear transformation. We have another rectified linear unit after it. And then finally, we're going to have a final linear transformation that goes from 512 inputs down to just 10 outputs. And those 10 outputs actually correspond to these 10 labels. So the idea is that we're going to want to train this network to have information flow through these linear transforms and eventually produce a vector where whichever element of that vector has the highest value, we're going to assume that that's the label that it corresponds to. So if we feed an image through and the highest value in that output 10-dimensional vector is the fourth one, we're going to go, okay, 0, 1, 2, 3. So this is the fourth element. So we would assume that it was address. Does that make sense? Okay.
Yeah, I'm just wondering, is there a standard way to parameterize, sorry, that, because if you change your target vector, that's gonna mess up.
Yeah, so typically you would put something like for example, if the input size changed, like you wanted to run this for a bigger image, you might put like image size here. And then instead of 28 by 28, you would have image size, something like that. That would be a totally valid way to do this. And in general, that would be how I would solve it. But I'll leave it like
and
this.
the same with y, I take it. So, and the same with
Yeah.
y, I take it. Yeah. Okay.
Yeah, exactly. Yeah. So obviously these are pretty flexible. This is like a linear operator that will convert any number of inputs to any number of outputs. And the more of these we put, the more complicated the network is, and the more potentially able it is to learn a lot of different categories. So for the forward calculation, we're just going to say x equals self.flatten. So the first thing we need to do is flatten the inputs so that it works with the rest of this network. And then we're going to get the results is equal to self.linear ReLU stack. Oops. Of x, and we can just return that. So the running these networks that we declared is quite simple, and that is all we need to define in our neural network class. So let's just make one and print it, so we can see what it looks like. And we see that it's a neural network. It's got this flattened layer, and then it's got our linear transformations here. All right, I see that it is now 10:30, so we're kind of out of time, but I'm just going to kind of quickly do the last couple items here since we're almost done. So I'm going to declare a loss function. This is a built-in loss function that is kind of pre-written in order to be good for exactly these kinds of classification problems. So I don't have time to talk about it really, but it's basically specifically made for these kinds of problems where you're trying to take an image or a bunch of data and convert it into a label. And then I'm going to make, again, a stochastic gradient descent optimizer. And we can just tell it that our parameters are model.parameters because this neural network class, which is a subclass of the module class, will keep track of its parameters for you. And I'm giving it a pretty low learning rate. And then I'm just, I wish I had time to walk through this, but I'm just going to copy and paste this code block here. So what this is going to do is we're just getting the size of the data set. And then we're going to walk through each batch number for X and Y. And we're just going to feed the inputs to the model. We're going to compute our loss. We're going to take zero our gradient and take our optimizer step, which we did earlier. And then this is just every 100 steps, it's going to print out a message about how it's doing. And the thing to keep in mind here is that in previous times we've iterated over the data loader, we've broken out of the loop so it didn't go all the way through. But this is actually going to go all the way through the data set and train it for every element. So let's just go ahead and run this. And once again, I apologize for this going so fast. But you can see that it's stepping through the data set. There's a total of 60,000 items in the data set. And we can see that the loss is getting a little bit smaller each time, and it's getting a little bit better. So the last thing we were going to do is just basically take that cell that we plotted earlier, where we made this plot, and we were just going to plot it for the trained model now using the test data to see how well the model does. So again, since we're out of time, I'm just going to copy and paste this code block. But this is basically the same thing. It's just going to kind of, there's a little bit of code here that will cause it to randomly select a set of images out of the data set. And then what it does is it runs our model prediction. And notice that it's using the test data, not the training data. But it's going to run our model prediction, find the label, which can corresponds to the maximum value in the 10 element prediction vector, get its name, and then print out the name that the model thought, followed by the true name. So that's what this looks like. And surprisingly, it did pretty well here. Now it seems to think that the sneaker and this sandal are bags. So it's not a perfect model, but it got this bag right and it got this coat right. So it's doing an okay job. And in fact, if we trained it on more data or we trained it for longer, it would probably do a lot better. But unfortunately, this is all the time we have. So I would encourage you, just as an aside here, pytorch.org/tutorials has a similar version of this tutorial we just went through and a whole bunch of other tutorials. I realized this was a lot that went very quickly, so if you have more questions, I'd encourage you to come to the office hours today, and I'd be happy to talk more about some of what we went over here. Unfortunately, I'm going to have to close this room shortly because I need to head over to the talk with JB Pauline. But I'd be happy to take any quick questions as long as they're quick. Otherwise, I'd encourage you to come to the office hours.
When are the office hours, sorry?
They are during, so I think they're right after the next talk, so at 11:30. They're during Dora's talk because Dora's talk is going to be on Tuesday now.
Oh, okay, thank you.
Right. All right, great. Thanks everyone for hanging through this. It went really fast. Again, I encourage you to come to office hours to ask questions. But for now, I'm going to have to close the room and I will see you in the next talk.